Okay, so this is the problem that we were looking at before the break. So let's get back to it. Hopefully this makes sense. Hopefully you remember this problem where we have two different sized pulleys that were connected by a belt. This belt really connects them, right? This belt is what lets you jump from one smaller pulley to a larger pulley. And how do you jump? You know that anything on the edge of A is the same as on the edge of B, right? The velocity on the edge of A, if it was 4, I don't think it is, but if the velocity on the edge of A was 4, then the velocity the belt is 4, and the velocity of this larger pulley on the edge of the larger pulley is 4. And so, I do like RA omega A equals RB omega B, or RA theta A equals RB theta B, right? Use the information that the velocity, and what is the velocity? R omega. What is the acceleration? R alpha. What is the distance? This arc length S, R theta. So R A theta A equals R B theta B if you want to jump from A to B. So we did that. We did kind of all the math at pulley A, and then I took my answer, 7.09, and I jumped it to the angular velocity of pulley B, and I used that to get the velocity of point P. All right, but then there were some other things we need to calculate. We found the velocity of point P. Let's find the acceleration of point P. All right, so my thinking is I need to kind of decide where I want to do my math. The first pulley I did kind of my math on pulley A, and then I jumped my answer to pulley B. So my instinct actually, okay, I see where I'm going wrong. My instinct is to do the math on pulley A, but actually, I don't have to do any equations. If you're given the acceleration, I was about to try to use a constant acceleration equation, and you're asked for the acceleration, then don't use constant acceleration. Don't do a derivative or integral just yet. If you're given the acceleration, let's just take that and jump that information. Let's take this 2 radians per second squared for the acceleration, the angular acceleration for pulley A, and let's jump that to the actual linear acceleration on point P. All right, so how do I jump from one A to B? Let's say I'm going to jump from A to B. Well, I would say RA alpha A equals RB alpha B. The radius for pulley A is 0.25. The acceleration, the angular acceleration for pulley A is 2 radians per second. And the radius for pulley B is 0.4 times alpha B. So from that, alpha B, 0.75 radians per second squared. So the acceleration of point P, if I know the alpha, is R alpha. R is the distance that point P is away from the center of rotation. I can see where the center is. So it's 0.4 away times its angular acceleration of 0.75 radians per second squared. So this would be 0.3 meters per second squared. So that is part of, I hope you see what I'm forgetting, that is part of the answer. That's the acceleration of point P. That's the R alpha of point P. That is actually only the tangential. That's a tangential of point P. But do you see that point P is on a circular path? Don't forget, when things are on a circular path, don't forget about normal acceleration. It still has some normal acceleration. V squared over R or R omega squared. Let's see if we could use either of these. We already found the velocity of P, 1.06. So I could do 1.06 squared divided by 0.4. Or I could do R omega. What was omega? If we go back to our notes, 2.66. 2.66 squared. Either of those, we'd get 2.83 meters per second squared. So that is the a normal at point P. So what is the acceleration at point P? Well, it's asking for the magnitude. Before we get the magnitude, we're going to square both of these, take the square root. Let's look at these directions. This A tangential down here at point P would be that way, right? 0.3 that way. You can tell that it's accelerating. This one is rotating clockwise. This one is also rotating clockwise. So this acceleration, tangential acceleration, would be right there to the left. And the normal acceleration, y'all know normal acceleration is into the curve, so it would be up right there. So, you know, maybe I would say that the acceleration, let me get my pen here. Maybe we'd say the acceleration is negative 0.3 in the I and positive 2.83 in the J. But it asks for the magnitude. We're going to square these, take the square root. So 2.83 squared, 0.3 squared, take the square root. It's actually very close to 2.83. 2.84 meters per second squared. That is the acceleration, the magnitude of the acceleration of point P. All right, let's look at the next problem. Right here. All right, so load B is connected to a double pulley by one of two inextensible cables shown. The motion of the pulley is controlled by cable C, which has a constant acceleration, keyword, of 9 inches per second squared and an initial velocity of 12 inches per second, both directed to the right. Determine the number of revolutions executed by the pulley in 2 seconds, the velocity and change in position of the load after 2 seconds, and the acceleration of point D on the rim of the inner pulley at t is equal to 0. All right, it's asking for a lot, isn't it? It's asking for a lot. And where are we going to start? Well, we were told that this acceleration right here of cable C is 9 inches per second squared, and a V initial of 12 inches per second, and a constant acceleration. If that rope has a constant acceleration, then my my pulley that it's connected to will have a constant angular acceleration. So I can use my constant acceleration equations, I can use my constant angular acceleration equations. Either of those would be good. So kind of thinking about that, I could do most of my math right here at C. I could actually take that initial velocity, that constant acceleration. I could, you know, find the after 2 seconds. I could find the distance of the rope C. I could do all my equations on C, and then I could jump those answers to D, from the inner pulley to the outer pulley, or I could go ahead and take all this information and jump it to the inner pulley or the outer pulley. I could do my equations on the pulleys. Or I could actually take most of those and jump it all the way to B and do constant linear acceleration equations on B. So you can decide. Sometimes some will make more sense than others, but you can decide where you want to do most of your math, depending on what's been given and what you're trying to find. All right, so I'm given a lot of information at C. Determine the number of revolutions of the pulley. Okay, so that's kind of like the theta of the pulley. The velocity change position of B, and the acceleration point D. I don't know if there's an easier place or a harder place, but you decide where you want to do most of your math and do either your integrals there or do your constant acceleration equations there, and then jump your answers to what it's asking for. I'm gonna want to do most of my equations for my pulley. So I'm going to jump this V initial and this acceleration to what's the angular velocity initial, what's the angular acceleration of the pulley. So how do I jump that? Well, if the velocity of point C is initially 12 inches per second, the velocity of D is also initially 12 inches per second. Could I jump that to the angular velocity? Could I jump that to the initial omega? Well, I know that V equals R omega. So if I know 12 inches per second, and I know I'm looking at point D, the radius is 3, then what is omega? I would get omega initially is 4 radians per second. All right, so let's talk about this a second. Is that the omega of the inner pulley or the outer pulley? We have two pulleys that are fixed together. Two pulleys that are bolted together, right? So they are moving together. So it's actually that there's only one pulley, one rigid body. This rigid body will only have one angular velocity, only one angular acceleration. The angular information for the inner pulley is the same as the angular information for the outer pulley. That was important. Did you get that right? The angular information of the inner pulley would be the same as the angular information for the outer pulley. Does that make sense? If the inner pulley rotates 2 revolutions, I think the outer pulley rotated 2 revolutions. All right? If the inner pulley rotates 25 degrees, the outer pulley rotates 25 degrees. Let's talk about radians. If the inner pulley is going at 4 radians per second, the outer pulley is going at 4 radians per second. Okay? Do not do this. I'm about to write something that I don't want you to write on your paper, so don't write this. Don't do this. It's not that the R inner omega inner equals R outer omega outer. This is not true, right? That would be saying that the velocity on the edge of here is the same as the velocity on the edge of here. That is not true, right? The further you go out away, the larger the velocity. All right, so we don't use this right here. We don't use this right here to jump from inner to outer. We just know that the angular information for the inner is the same as angular information for the outer. It's the angular information for the pulley, and they're bolted together as if they're one pulley. Okay? All right. So let us jump this acceleration. If I know the acceleration, the tangential acceleration of point D is 9, a constant 9 inches per second squared, and A equals R alpha, then this 9 equals alpha. So alpha would be 3 radians per second squared. So that's the alpha for the inner, the alpha for the outer. And it told this was a constant. This was a constant acceleration. Okay. So now, if I know that I have an initial velocity of 4, a constant acceleration of 3, after a time of 2 seconds, what would be the number of revolutions executed? I could go to my constant acceleration equations and decide which constant acceleration equation, if I know the initial velocity, the acceleration, the time, what equation could I use to solve for how many revolutions? You could look at those. You could trial and error. How about this? The theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. Because I'm going to either assume this is 0 right here, or just break that over to a delta theta, and I can find the change in theta would be equal to, let's see, I know that this is 4, just a second, I know that this is 4 after 2 seconds, this is 3, 2 seconds, so 4, 2, 1/2, 3, 2 squared. So the change in theta would be 14 I'm having trouble with my pen here. 14 radians. That's not what the question asked for. It asked for the number of revolutions. So just convert radians to revolutions. I know that 1 revolution is 2 pi radians. 2.23 revolutions. 2.23 revolutions is revolutions for that pulley. Okay, so we answered that. We answered the number of revolutions. Now let's find the velocity and change in position of load B. Velocity and change in position of load B after 2 seconds. Let's start with 1. Let's just focus on the velocity. The velocity of load B after 2 seconds. Well, I'm not sure about the velocity of load B, but I bet I could find the omega of this pulley, this rigid body, and then maybe I can kind of convert that or change that to the velocity of this point, which would be the velocity of load B. So I might say, first let me find the angular velocity of the pulley after 2 seconds. Right, that's kind of step 1. That's funny. Angular velocity of the pulley after 2 seconds. How could I find that? Well, this one doesn't have final angular velocity, but one of those other constant acceleration equations might have the final angular velocity. How about this one? Omega final equals omega initial plus AT. Second here. Omega final equals omega initial plus AT. Omega initial. Okay. I'm having trouble here. Omega. Alright. Omega final equals omega initial plus alpha t. Omega final is what I'm looking for. It started with an initial velocity of 4, angular velocity of 4. Has a constant acceleration of 3 after 2 seconds. So 10 radians per second. Look, not square. 10 radians per second would be the angular velocity of the pulley after 2 seconds. But it wanted the velocity of load B. Well, let me first find the velocity. Let's call this maybe point F. Let me find the velocity of point F. Velocity of point F, let me go to a different page, is our omega, right? It is 5 inches away from the center of rotation, and the omega would be 10 radians per second squared, so 50 inches per second, not squared, 50 inches per second up is velocity of F, which is also the velocity of load B. Okay. It also asks for the change in height of load B. Change in height of load B. Let's think about that. Let's talk about that. Do you see that if B, the change in height of load B would be this arc, whatever arc on the outside of this pulley, whatever the arc length is on the outside of that pulley after 2 seconds. What is the definition for arc length? S equals R theta. What is the theta that it traveled, it rotated after 2 seconds? I found that one was the 14. I can reuse that. All right, good. So let's find the change in height. So this would be the S. S is R theta. R is 5 inches. Theta needs to be in radians. 14 radians. So this would be 70 inches would be the change in height of point B. All right, one last thing that it asks to answer. It's kind of weird. It's asking for lots of different things. What is the acceleration of point D on the rim of the pulley at not T final, but T initial. What is the acceleration of point D on the rim of the inner pulley? Okay, well, I was almost practically given this. All right, the acceleration of cable C is 9. It's a constant 9. That's at T is equal to 0, T is equal to 2, T anywhere in between. So the acceleration of point C is 9 inches per second. So what is the acceleration of point D? That's almost it. That's practically it. The acceleration of point D, 9 inches per second squared. But what am I forgetting? What am I forgetting? Neglecting? That is only the tangential acceleration for point D. I also need the normal. Anytime something's in a circular path, don't forget about normal acceleration. So the normal acceleration for point D would be, I need v squared over r or r omega squared. And also this is only the initial, and I think it gave me the initial 12 squared over 3. 48 inches per second squared. So it's asking for the acceleration of point D. Last problem, I squared these and took the square root because it asked for the magnitude. If it had asked for the magnitude, then I would square those and take the square root. If it asked for the acceleration, I don't want the magnitude. I want you to leave it in i's and j's. Leave it in i's and j's. So this 9 would be right there in the I direction. We were lucky that this was at the very top of the pulley. It's just in the I direction. And the 48 is in the normal direction. That is into the curve. Into the curve. So I would say the acceleration for point D, 12I minus 48J. Why minus? Because J up would be positive. This is down into the curve. I need some units right here. Box in my answer. Box in my answer. Now let's talk about this. We were lucky that that point was just at the very top, because I could break that up into I and J really easily. But what if I wanted to know, hey, what's the acceleration of this point? Let's call it point G. What's the acceleration of this point? Well, the acceleration of this point, and let's give it some angle. Let's say this is at 50 degrees below horizontal. We've got to mention this. Let's talk about this. The acceleration A tangential would be right here. And if this radial line is 50 degrees from horizontal, this is perpendicular to it, this would be 50 degrees from vertical. And so I might need to break that tangential acceleration into its I and J component. And then its normal acceleration would be into the curve right there. I might need to break it into its I and J component. So if you're lucky, then maybe at the very top, very bottom, very right, very left, and your normal and tangential are easy to see. They're completely in the I and J. But if you're unlucky, if you're at an angle, you need to be able to break that up into their components. Be able to break that up into their components. We'll go over into this a lot more in detail later. But we were lucky. It was just at the top. All of the tangential was in the I. All of the normal was in the J. And it was in the negative J because it was into the curve. Okay. One more problem in this section. We can do this. Alright, for a short period of time, the motor turns gear A with a constant angular acceleration of 4 radians per second squared starting from rest. Determine the velocity of the cylinder and the distance it travels in 3 seconds. Alright. So, here we have a constant angular acceleration. We haven't looked at this before. We've got two, actually they're gears, right? They are gears. They're not connected by a rope, but it's kind of similar. Now, they are gears. How can we kind of jump from this smaller gear A to this larger gear B? You might say, well, I bet it's a ratio of the radiuses. Yes, absolutely. How can we jump? If these teeth are kind of, moving and interconnected right here, don't you think that the velocity on the edge of gear A is moving with the same velocity on the edge of gear B? Does that remind you of the belt? It's the same thing. Right? All the linear information on the edge of A is equal to the linear information on the edge of B. That's how we're going to jump from A to B. All right, my second thought is, where am I going to do all my math? I see this word constant acceleration. So I'm either going to use linear constant acceleration equations. I actually could do all my math on C, or I could do all my math on pulley A, or I could even do all my math on pulley B. You could do either three of those. Just decide what are you given, what are you asked to find. We're given a lot of information about A. Well, not a lot of information, but this angular acceleration for A is given. Maybe I just do my constant acceleration equations for A, and then I jump my answers from A to B, from B to D, from D to C. Or I could do them on B, or I could just take this 4.5, jump it all the way to C, and I can do linear equations on C. I think that one might be the easiest and quickest, but I don't know. For some reason, I've decided I'm going to do my math on B, on pulley B. So first, let me just jump this 4.5 radians per second squared to the alpha of B. How do I do that? Well, RA alpha A equals RB alpha B. 75 4.5 equals 225. Alpha of B is a constant 1.5 radians per second squared. All right, so I know that it starts from rest. I mean, if gear A starts from rest, then B starts from rest, C starts from rest as well. And I want to know first let's find the velocity. I want to know the final velocity after 3 seconds. So looking at those constant acceleration equations, kind of reminding myself, I'm looking at disk B. I'm looking at disk B. How about this one? Omega final. I know omega initial is 0, starting from rest. And I know my alpha, I know my t. So just remind yourself, where are you looking? This is the omega final for disk B, the initial for disk B, the alpha for disk B. Time, of course, is just the time throughout the problem. Doesn't matter if you're looking at A, B, C, or D. All right, but anyway, the omega final for disk B would be alpha 1.5 after a time of 3 seconds, 4.5 radians per second. All right, so I need to jump that to the velocity for cylinder C. All right, so that is, I would call this the angular velocity for disk B. Disk B, though, I kind of need to jump it to the inner, but there is no jumping from outer to inner, right? This is a smaller pulley and a larger pulley that are glued together. They're fixed together. They're moving together. So any angular information for B, so omega B is 4.5. That is the same angular information for that inner pulley D. All right. And now if I know the angular information for the inner pulley D, then I can find the velocity on the edge of D, which is the velocity of C. I would say the velocity on the edge is R omega. The velocity of C would be, now let's be careful, use this R, 125 millimeters 125 millimeters times 4.5 radians per second. I haven't been very careful with my units. So I'd get the velocity of C is 563 millimeters per second. So let's look back and see what I did. I decided to do my math at B, so I jumped that alpha of A to an alpha of B. I did my constant angular acceleration for B, and then I took that and I jumped it to the linear velocity for the cylinder C. Alright, then it also asks for the distance it travels. Okay, well, how about I find the theta that B goes, and then I can kind of convert that to the distance that the cylinder goes. All right, so sticking at disk B, just looking at any of those other two constant acceleration equations. How about this one? Theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. Again, I'm looking at B, so this is all for B. It started from rest, and we can just either assume it starts from at a zero orientation, or just bring that over and say the change in theta. So the change in theta for disk B will be 1/2. Oh, sorry. Make sure I use the alpha for disk B. 1/2, 1.5 a time of 3. So 6.75 radians. That's the theta B. That's the theta D. Now, how to convert that to the distance that the cylinder moves? Well, so for a second here, let's talk about directions. This is going clockwise, so this is actually going counterclockwise. So this would be going up. So let's find the arc length. Let's find the arc length that inner pulley D moves, right? Because that arc length would be also the height that the cylinder moves. If I know the theta, then I can find that arc length. Arc length S, S equals R theta. So this would be 125 millimeters, 6.75 radians. Oops. So 844 millimeters would be the height of C. Would be the height of C. Okay. It's taken us a while, but we have finished this section for rotation. And so I'm assigning the homework today. So today's lecture is for Wednesday, March 18th. So I'll give you 2 class dates. So that means this is due on Monday, March 23rd. Monday, March 23rd. Now remember, do it exactly like you would have done it. Do it on engineering paper. Format it correctly. Tim is still going to grade it. And you are going to upload it in the homework. Let's look at the homework. So homework 11, due Monday, 3/23. You're going to upload it in the homework 11 assignment inside of Canvas. Upload it as a PDF, right? Try to make it a nice PDF, a good PDF. You know, take a good picture of it with a smartphone. If you have a scanner, that'd be great. Scan it in as a PDF. Save it on your phone, save it on your computer, and then upload it into Canvas as your homework. Do that by midnight, we'll say, on Monday, March 23rd.